So, welcome students in this session of classes where we are taking up geometry for IOQM. Now, what we have gone through till date is up to say common tangents to circles. In the last lecture we did common tangents to circles. Prior to it we started with circles and theorems related to it, and prior to it we had done other things also. Okay, now moving ahead, let us now go through some stuff related to say tangents itself, common tangents itself. We read one or two things, followed by in today's lecture what we are going to do is some remaining stuff of circles, Ptolemy's theorem, and moving ahead to say polygons, okay, especially regular polygons. So, now let me start with Ptolemy's theorem. Okay, I think Ptolemy's theorem is something that we So, what does Ptolemy's theorem states? That in a cyclic quadrilateral, the product of opposite sides, rather the sum of product of opposite sides is equal to product of the diagonals. What is the theorem? The sum of product of opposite sides, that is say AB into CD plus AD into BC is equal to product of diagonals AC into BD. This is the theorem named after the mathematician Ptolemy. It will help you in solving lot of situations when quadrilaterals are involved. Primarily it is helpful in length chasing. If you are asked regarding length, some of the data is provided, some is not provided. But as always, the first thing that we are going to prove is just to establish it. Just remember basic, there are a lot of ways to prove it. One way is that what we do is that we draw a line. Yeah, we take a point, say P. Let me change the color. We take a point P on BD and join AP. Just appreciate the manipulation that is being done. Okay, we have taken a point P in such a manner that these two angles are equal. Okay, one of these two angles would be larger. We are assuming that this one is larger, BAC. Now, we are saying now take a point P and draw a line like this such that these two angles are equal. Now, what does this does? If you are able to see this angle is the angle subtended by chord AD is equal to this angle, isn't it? Angle subtended by chord AD at the circumference. So, these two angles are going to be equal. Fine. As a consequence, this angle BPA and this angle, they are going to be equal. So, what you are getting is triangle ABP triangle ABP is similar to ABP is similar to triangle ACD, isn't it? Now, if you see carefully, and therefore, what are you going to say? AB upon AC is equal to BP upon AD is equal to BP upon CD. Or rather, what we do is that let us write it like a AB into CD. This is what we are looking for, is AC into BP. Let us call this as our first expression, okay, first equation. Now you are able to, I think now you are able to fathom what we are going to do next. Now if you are able to see this angle, watch very carefully, this angle and this angle are equal. Are you getting it? Say if this is some theta, this is alpha. So this pink angle is theta plus alpha. This is theta, then this pink angle is also theta plus alpha. So these two angles are equal, and similarly, what we can say is that this angle subtended by chord AB. Okay. So as a consequence, the third angle here they are similar, they are equal. Hence the triangles. Now let us write again which two triangles are similar. A, B, C and A, P, D. The triangle APD is similar to triangle APD is similar to triangle ABC. So therefore, what we can now write? BC. BC BC. Let us choose properly. Triangle AD. AD upon opposite to this angle is AD, opposite to this angle is AC. AD upon AC. See, we have already got BP, not what we want is PD. And PD is opposite to this angle is BC. AD. Okay. So it will be PD upon BC. Meaning thereby AD into BC is AC into PD. Okay. So by 1 and 2 you are able to see AB into CD plus AD into BC. What is it equal to? AC into BP plus PD. What is BP plus PD? BD. So this is what our Ptolemy's theorem is. Again, this is why I have always insisted that you should all try to prove things for the simple reason that once we are aware of it, once we make use of these, once we get accustomed to the proofs, what helps, it largely helps you in dealing with problems. See, a beautiful construction was thought of to justify it. I am not saying that this is the only way, there are other ways to establish it, but using pure geometry, we have just considered a point. So, later on in problem solving, this thing can be thought of. There can be points of time where in dealing with a problem, you consider a point. Let us consider a point such that this angle is equal to this angle. And then we have proceeded. So, it has given you one way to explore a possible geometrical situation. So, always try to remember to recall how have we initiated the proofs of the basic theorems that we have encountered right throughout geometry. That will give you a very good platform to start solving problems. Because what is the general thing, what generally occurs is that we are not able to initiate. We may know a lot of facts regarding certain, regarding circles, regarding triangles, regarding quadrilaterals, but based on a certain piece of data, how do we initiate the solution in such a manner that we get the desired things. It is not possible that if I know 10 facts about circle, I do it one by one always. So, therefore, it is very, very, very important. I am probably for the 100th time in last few lectures I am saying, always remember how we started the proofs of the theorems that we have gone through, so that you have various ways of initiating the problems. Okay? Now, this is the theorem. Now, what are few problems that we can do regarding it? Say, so the question is, if ABC is an equilateral triangle and P is any point and P is any point on arc, say AB. On arc AB. Sorry, let me write it properly. On circumcircle of triangle ABC lying on arc AB. Find, let me make it a numerical problem. Find PA plus PB upon PC. P does not coincide with A, B, C. Okay. So let me draw an appropriate diagram. Whenever you have to draw circumcircle of a triangle, draw a circle and inscribe a triangle in it, rather than drawing a triangle and then circumscribing a circle about it. Okay, now ABC. We have taken a point P on it. So PA PB, we are being asked to show that PA plus PB is PC, isn't it? Now you can see PACB is a cyclic quadruplet. So therefore, by Ptolemy's theorem, what can we say? See, product of opposite sides, AC into PB plus BC into PA is equal to product of diagonals. What is it equal to? Product of diagonals. What is that here? AB into PC. So, since it is an equilateral triangle, PA plus PB is PC. So this is what have we got. Now insofar as the question is concerned, answer is 1. Well, we could very well have thought it that if P coincides with A, PA is 0, PB and PC are equal. Okay, that is one way we could have done it, but just an application of Ptolemy's theorem. Moving ahead, suppose, let me take one more problem, say, find the ratio of length of diagonal to its side in a regular pentagon. Regular polygons we have taken up, we will take up as we move ahead, even hopefully in this lecture only. I'll try that we take up in this lecture only, but I think regular quadrilateral is square. Regular pentagon means a pentagon, all whose sides and all whose angles are equal. Now in case of a pentagon, if you see, I am drawing its circumcircle, okay, and what I am saying is that see, all its sides are equal in length. All regular polygons have a circumcircle, followed by, see, if you look at its diagonals carefully, This is a diagonal. Okay. This too is a diagonal. You can see by symmetry that these two diagonals are equal in length, and so will be the other diagonals. So, if these lengths are y, okay, we can draw one, say some more diagonals. That is not a big deal. Say let me draw one more diagonal. This will also have length y. Now, if I think you are able to conceive what we are going to do. We are going to consider a cyclic quadrilateral. Say I consider the quadrilateral A, B, C, D. Okay. Consider A, B, C, D. Quadrilateral A, B, C, D. So, by Ptolemy's theorem, what we have AB into CD, sorry, AB into CD plus BC into AD is equal to AC into BD. Now, as with every diagonal, so with this diagonal, this length is also y. See, you are able to see the symmetry, isn't it? If for this diagonal, there is one vertex to the left of it, two to the right of it. Draw a diagonal. There will be one vertex on one side and two on the other side. Just by symmetry, I am saying they are all of equal length. So, AB is x, so is CD. BC is x, AD is y. AC is y, BD is y. To its side. So, we have to find y by x. So, dividing it by x square, what do you get? The golden ratio. This is the answer. So, what is to be kept in mind is that not only square, in square also both the diagonals are equal in length. There is one more regular polygon in which all the diagonals are equal in length. Okay. Square and pentagon are two regular polygons. Square and regular pentagon are two regular polygons in which all the diagonals that you draw are of equal length. You can see in pentagon you can draw 5 diagonals. I have drawn 1, 2, 3, 4. One diagonal I have drawn. You can draw 5 diagonals. Okay. So, this is how we use Ptolemy's theorem. I have taken rather simple examples. As we move ahead, we are going to take some good problems where Ptolemy's theorem would be utilized, especially in case of circles. If we are dealing with length of sides and diagonals in a cyclic quadrilateral, it plays a very important part in dealing with problems of that nature. Fine. Now, one or more important things that we need to know. Once in a while you may come across circle of Apollonius. It says if A and B are fixed points and P is a moving point such that PA upon PB is equal to K not equal to 1, then P lies on a circle. PA by PB is a constant. This circle is called circle of Apollonius. Again, a very fantastic geometric problem. There would be other algebraic ways once you go through coordinate geometry to deal with them. But in geometry, it is done fantastically by angle bisector theorem and stuff like that. We will find what the radius is, what the center is. Okay. So, what we are given is that PA by PB is K. Now, suppose, so let me draw the diagram in a separate page. Suppose A and B are, you are given that A and B are two fixed points. Okay. So, this is some point P. PA is to PB is K is to 1. Now, on segment AB, suppose this is 2 is to 1 for example, there will be a point Q which divides AB in the ratio 2 is to 1. And there will also be a point R such that this will be equal to AR by RB. Okay. So, what we are saying is that we can also take our point P to be this point, we can also take our point to be this point. Now, by angle bisector theorem, what we can say is that if PA by PB is AQ by QB, then PQ is the angle bisector. Angle bisector divides the opposite side. Angle bisector divides the opposite side in the ratio of sides containing the angle. So, therefore, Q must lie on the angle bisector of APB. In similar vein, we can extend and say that the external angle bisector divides the opposite side externally in the same ratio. That means, say, now we know, what do we know? We know that the internal and external angle bisectors, are mutually perpendicular. They are mutually perpendicular. That, see, Q is a fixed point on AB, R is a fixed point on AB, and what we are getting is that angle QPR is always going to be 90 degree. So, what have we read? Angle in semicircle is a right angle. So, therefore, Q lies on circle with P lies on circle with QR as diameter. Fine. So, you have to think in a slightly nuanced and a different way while dealing with problems of geometry. This is called circle of Apollonius. you can say midpoint of QR, whatever that point is, say S, midpoint of QR is the center, and what is its radius in terms of AB and K. So, we can say that see, what is this length? AK is to KB is, AK is to QB is K is to 1. So, K by K plus 1 times AB, okay, and this is 1 by K plus 1 times AB. Now, AR, what is the AR is to BR, you can say AR upon BR is also K upon 1. So, subtract AR minus BR upon AR, we have to find B upon BR is, what is AR minus BR? AR minus BR is AB. So, what is BR? AB upon K minus 1. We are assuming K is greater than 1. So, BR is 1 by K minus 1 times AB. So, radius of the circle this distance AB, what is this distance? Now, if you add 1 by K plus 1 by K minus 1 is 2K by is K upon and K is greater than 1. Okay. So, this is what you are going to get. Again, it is a beautiful combination of two things, one the angle bisector theorem and the other the angle in semicircle is right angle. By combining these two, you are able to do it. Okay. This is something that we will, as we move on, be required to utilize in solving problems. There are various things that we have accumulated in our study of geometry, especially in these classes, and also prior to it when you have gone through your regular school classes. A demanding problem or a problem which requires a bit of ingenuity are those problems where they combine 2 or 3 notions, 2 or 3 generally known and utilized notions in a single problem, and that creates an issue. How to start, how to initiate. Okay? Now, don't try to remember it. If you have the ability to recall how are we getting to this point, then we have ample time in exams like IOQM to come to this point. Okay? So, generally somebody may ask you what is the radius and stuff like that. Okay? Just I wanted to make you all know this fact also, because it is a beautiful combination of angle bisector theorem that we have read in triangles and this. Fine. Now, moving ahead, let me give you a question. Okay. Quite unrelated to this, to stuff that we have gone through. Just I was going through something, and I found a problem which said related to circles, and then I will come to something called radical axis. Okay. So, what we are given is that we are given a diagram. Let me draw the diagram. And common chord of these two circles is also drawn. Centers O1, O2 is given. So, let this be A, let this be B. Now, we are given a point P on this line, and from this point P we are being told that tangents are drawn to these two circles. So, these points are Q, R, and say this is M. Okay, since it is the common chord, okay, line joining the centers will be bisecting. Fine. Diagram I have this 90 degree need not be given. The question said if AM is equal to 2, AP is equal to 4, find PQ. Find PQ plus PR, because that is common to all of them. This is our question. Okay. So, how do we proceed? This angle is 90. We simply draw PO1. Okay. So, we can say if this radius is R1, what can we say? O1P whole square is PQ square plus R1 square. Okay. Further, in this right angle triangle, we can say this is equal to MP square, is it not, plus O1M whole square. What is O1M whole square? This is also R1. So, you can say PQ square plus R1 square is MP. MP, I think length is given. AM is 2 and AP is 4. So, this is 36. What is O1M whole square? O1M whole square is R1 square minus AM square. Is it not? What is O1M square? R1 square plus AM square. R1 square gets cancelled out. What you get is 36 minus AM square. What is AM square? 4. So, this is 32. PQ square. So, PQ is 4 root 2. Now, if you are able to fathom that we are going to have similar calculations here. is it not? We are going to have similar calculations here. This is 90 degree and I am going to say PO2 is, I think I am not writing it, O2 P whole square is PR square plus R2 square. It will be equal to MP square minus O2 M square. We will write R2 square, R2 square will get cancelled out. So, what we learn is PQ is PR. So, PQ plus PR is 8 root fine. So, this is what we have. So, this line, the common chord in a circle is called radical axis of these two circles. Okay. Length of the tangent drawn from are equal. If you keep this in mind, it might on occasions be of help. In the case the two circles are intersecting, it is nothing but the common chord. Of course, from a point inside you won't draw circles. That to generalize it, what we say is to generalize it from point inside, you can say how can you draw a tangent. So, to generalize it, what we say is that radical axis is set of points whose power with respect to two circles are equal. What is power? I hope you are able to recall. I believe I have told you once. If the point is outside or inside, the expression is same. If this is O P, so power of point P, say this circle is some omega. So, power of point P with respect to omega is equal to OP square minus R square, where R is the radius. So, what happens is that if the point is outside, you can say OP square minus R square is length of the tangent. Of course, if it is inside, then this is not the length of the tangent, okay. But if it is outside, it is length of the tangent. So, PA into PB, if you remember, PA into PB is PT square, we proved that. That is power of the point, PA into PB. For internal point 2, we say PA into PB is equal to the power, but then what happens is that for an internal point, we talk about sensed magnitudes, okay. If this is PA is positive, this PB we say is negative. in that case it works. For internal points, PA minus PA into PB will be R square minus OP square. What I am trying to say is that suppose there is a point P inside and you draw a chord like this. So, I hope you PA into PB we have already gone through is PC into PD, is it not? Now, if P is the midpoint, O is the center, so what is PC? What is PC or PD? This is R square minus OP square. We may say it is OP square minus R square if we say, suppose if this side is positive, PD is negative. That is called sensed magnitude, we do not get into it. But even when the point is inside the circle, this is useful. And therefore, if the point is inside the circle, we say power is negative. We always take power to be OP square minus R square. So, if the point is inside, it is negative. If the point is outside, it is positive. So, for outside points, what do we get? For outside points, what do we get? That the root of power is nothing but length of tangent. And thereby we say if the two circles are intersecting, their radical axis is the common chord. Radical axis, in fact, you can understand very easily, I think, that power of this point is going to be these points where they meet. So, our radical axis has to pass through this. Incidentally, it is a useful thing for the simple reason that incidentally they are nothing but, it turns out to be nothing but a straight line. So, there will be other properties of a straight line that we will be required to use. It is a straight line that makes the whole situation fascinating, okay, which is perpendicular to the line joining the centers and stuff like that. In algebraic geometry, coordinate geometry, you will see how it is utilized in different manner, okay. Now, in so far as the theoretical content is concerned, we have tried to cover almost everything. Angle between the circles or orthogonal circles are when the angle is 90 degree. So, angle between circles, but for that we need trigonometry. Let me only tell you orthogonal circles. And then any arbitrary angle we will take care of later. So, even at the point of contact, tangents pass through centers. Okay. If somebody is asking you to find the length of the chord, you can very easily find it. Orthogonal circles, that means the circles, the tangents, rather the normals or tangent, the radii at the point of intersection are perpendicular. This is what orthogonal circles would mean. That means the radii of this circle would be tangent to this one, and the radii of this circle would be tangent to this one. What you can see is that if somebody asks you to find the length, you can very easily find it. I hope I am very clear. Area would be half R1 R2 is half, suppose this is PM into O1 O2. So, PM is R1 R2 upon O1 O2. So, length of the chord PQ is going to be See, these are all problems. You don't have to remember these results. Draw a diagram, draw a worthwhile diagram, 90-degree stuff, and you can come across these things. I wanted to take up polygons today only, but I thought that the time available was not good enough. So instead, I told you something about circle of Apollonius, then radical axis, and then orthogonal circles. Next class will deal with polygons and circles related to polygons, then something about trigonometry. I hope you know the basic definitions of trigonometry. We will extend it and see that how it is utilized in problems of geometry, because geometrical intuitiveness on occasions is very demanding, just like if you recall the proof of Ptolemy's theorem, circle of Apollonius. Those stuff required a bit of ingenuity, a knowledge of how things work. Probably you may have a perception that you can only deal with them if you know them beforehand. So that sense takes time to develop. If we start using algebra, trigonometry, on occasions we are more accustomed and used to it, and therefore what you find is that when you use them, because we use the algebra in almost every domain, you feel more comfortable, and you also have additional tools to deal with the situation at hand, whether it is geometry or anything else. So at this point we are completing this lecture earlier for the simple reason that in 4, 5, 10 minutes it will not be proper for me to start polygons and then move ahead with trigonometry, even though at the beginning of the lecture I did inform you that we will probably be taking up polygons at the back end of the lecture, but it could not be because that much time is unfortunately not available. Okay. So, I hope in this unique series of lectures you are gaining something and it is helping you in preparations. But the most important aspect, I have always been telling you, practice, practice and practice. Practice the problems. Further, as I have been telling you, and again for nth time I am saying, if you are going through any proofs and stuff like that, try to prove them on your own. Just don't look at somebody solving it, pen it down once by looking at it and then try to pen it down on your own. That will be the way to remember it. So, okay, best of luck and thank you very much.